All right, so now that we have some of the lingo down, let's go ahead and take a closer look, as promised, to solve case 1. All right, and to solve case 2, we're going to use what's famously known as the law of sines. And so let me go ahead and share what that law is. We'll prove it, we'll take a look at it, and then obviously we'll use it. So the law of sines. What we're going to do is take any triangle ABC. Now remember, capital A, capital B, and capital C, those are our angles. All right, those are our angles involved. So what I'm talking about is I've got some, it could be right, it could be oblique, it could be whatever I want, right? But I have some triangle with, right, angles A, B, and C respectively, right? And then what's going to happen is we have sides, little a, little b, and little c. So recall, across from angle A is side A, across from angle B is side B, and across from angle C is side C in lowercase. So it turns out that when we have any triangle, right or oblique, right, it turns out that the ratios, if I take side A and divide it by its sine of its angle A, that ratio is the same as side B divided by the sine of angle B. And more, keep going on, right? The ratio of sine A, the ratio of side A divided by the sine of angle A is equal to the ratio of side C divided by the sine of angle C. And then by the law of transitivity, we can replace this with B. And so side B over the sine of angle B, that ratio is the same as side C and the sine of angle C. And more succinctly, if we just put all the ratios together, we're saying that all these ratios, side divided by the sine of its angle, is equal to the ratio of another side with its sine of its ratio. You can also equivalently rewrite this. You can, because of reciprocals, if I took the reciprocal of this, right, the sine of angle A divided by side A, that would be also equal to the reciprocal of sine B all over side B equals sine C all over side C. So this is actually the way that I like to write it, but I think the book writes it this way. So we can use any one of these ratios to basically set up a situation. And as we saw, case 1 and case 2 can be solved that. We're going to see a lot of this in 7.1, and we'll take a look at that in 7.2, and I'll show you how in a moment. But what I like to do is give you a little bit of proof of why this works. So what we saw way back when, I think when we were solving right triangles and situations, we can take our oblique triangle and break it up into 2 right triangles. This is pretty easy to do because I'll just basically bisect the angle C, and I have 2 right triangle situations. We'll call that the height of the triangle. Actually, it's height. So with that situation, because I have 2 right triangle situations, what I basically have are 2 ways where I can basically use my old sine and cosine functions. So sine, right, of angle A is the opposite, which is H, over the hypotenuse, which is B. And so multiplying both sides by B, we get that H is B, side B times the sine of angle A. All right, and then we could also do it for this situation, right? On this side, for this right triangle, the sine of B is the opposite divided by the hypotenuse, which is A. Multiply both sides by A, and we get that AH is side A times the sine of angle B. And so since both of these are equal to H, we can put them together, right? So that means that B times the sine of angle A is A times the sine of angle B. And then, of course, if we multiply both sides, let me change colors. If I multiply both sides by, or divide both sides by A over B, in this case the B's cancel out, leaving us with the ratio sine of A, right, over side B. And over here the A's cancel out, leaving us with side B over, sine of angle B all over side B. So I basically proved that route right there, right? And the proof basically follows because we can use the same idea, right? Let me try to redraw that situation again. So if I redraw that, right, side A, side B, sides, angle A, angle B, angle C, and their respective sides, right? The reason why this proves is we can bisect the angle A, right? Do it in such a way where we have a right triangle. Maybe it comes out over here somewhere, but we end up getting the same ratios. Kind of harder to draw that other situation, but I can do the same situation, or even with angle B, have my H have two right triangles and have the same situation. So that's basically the heart of it. Maybe I shouldn't have drawn an obtuse triangle, right? If I have drawn an oblique triangle that's not obtuse, it's a little bit easier to see those ratios. But those ratios will be the same, giving us the same ratio that we have over and over and over again. So I apologize. Maybe I shouldn't have drawn obtuse angles, but there's your proof. All right, and so we've got basically a nice law of sines that can help us solve not just right triangles, but oblique triangles. Of course, if it was a right triangle, we use our right triangle ideas that we learned way back in the day. But if it's an oblique triangle and it's case 1 or case 2, we'll use the law of sines. So now that we've established the law, let's go use it and solve some oblique triangle situations.